forces, about momentum, whether translational or angular. Now, let's talk about something slightly different. I've skipped chapter 12, which is to do with equilibrium, and came to gravitation because I think it's something new and a bit more exciting for most people. Now, the photo you're seeing here is what general relativity describes, what gravity is. And if we have time towards the end of the lecture, I'll actually go with a very quick or non-examinable, just overview chit-chat session about it. But first thing first, there's a famous story. Okay, a very, very famous story about Newton and apple. Not this kind of apple, just this kind of apple. Apparently, Newton was reading a book under a tree, and an apple fell on his head, and that hurt his head, and it got him starting to ask, okay, why did this apple fall on my head and not just stay there floating? Or why didn't it go up? Why did it fall down straight up on my head? And apparently, that ended up with Newton's laws of gravitation. Yes, that's a common reply. If he had ate the apple, we would have had much less physics, but then we would also have way, way less technology today. Okay, it's amazing how much technology came because of these thinking. So before Newton, there are actually quite a few attempts at describing how Earth works. Okay. It started, although most people attribute gravity equals, Newton, the apple falling on his head, it actually started much, much longer. Yeah, the first person, we don't really know who the first person is, but in history, the first person in history that we sort of can see in a reliable text is Aristotle. Okay, and that was about 384 before Christianity. So now we're in year 2020. This was year minus 384. Okay, and these philosophers, started thinking, it was the nature of rocks to be with Earth and the nature of fire to go up to the heavens or to the hell. You had other people like Brahmagupta in minus 665, who thought, okay, Earth was a sphere. There was no proof that it is a sphere, but they thought, okay, you know what? Earth is a sphere, and objects naturally liked spheres because they look nice. So everything wanted to come to the center of the sphere. Now, that aside, the motion of the sun, the moon, the planets, how do they move? I mean, okay, if you live in Muscat, you can't really see it. But if you live outside Muscat and it's a bit dark at night, you can see the stars. Okay, and they're really, really beautiful. And they're not only beautiful to us now, it has been beautiful and captivating for people throughout thousands of years. And they have spent a lot of time looking at them. Okay, and Ptolemy, back in, minus 100, minus 90, 90, not minus 90, about 90 after Christianity, okay, described with amazing accuracy, how long these planets take to move, and, how do we explain their movement? Yes, exactly. But in Arabic, his name is Batlimus. Okay. Now, you fast forward about 1,200 years, 1,300 years, and you had Nicholas Copernicus, okay, who was the first person to challenge Ptolemy, because Ptolemy, although he gave us these amazing calculations, he had the point of view that the universe is geocentric, which means that the sun is in the middle and everything rotates around this. Sorry, the earth is in the middle and everything rotates around the earth. Copernicus came and said, you know what? No, I don't think that's correct. I suggest a heliocentric system where the sun is in the middle and everything goes around the sun. Now, these were supported by people like Tycho Brahe, Kepler, and the very famous, that you might all know, Galileo. Okay. And Hooke, the same guy from Hooke's law. Now, these people started working and all of these people were working in different dimensions. Okay. Not until the brilliance of Sir Isaac Newton, okay, wasn't that he just thought about the apples and why it's falling. It's that he actually connected the two things together. Planetary motion, why planets move around the sun, and why the apple falls down towards the earth. Okay. Now, after that, Einstein came and did the theory of gravity and general relativity in 1916, and that is a different story. But the point being is, the reason why we keep saying Newton, although all of these people did it before him, is because Newton was the first person to connect the dots, okay? That things go around the sun and things fall towards the center of the earth for the same reason. So what is Newton's law of gravitation? Well, we have an apple and we have Earth, okay? And we know that if you drop an apple, it drops towards the Earth, right? This much we know. But there was another rule of Newton, Newton's third law. Do you remember what was it? It said that forces occur in pairs. So if that rule is still true, that also means first that everything is attracted towards Earth. But not only that, but also that Earth is attracted to these objects. Like this. Okay. Now we go one step further. Newton said, this is not special for Earth or for the sun, for planets. This is actually a general rule for any object that has mass. So objects are actually have gravity on each other. Okay, no matter how far away they are, they actually act on each other. So far, so good? Anyone has any questions so far? Okay. Okay. So let's come to a mathematical formulation. The law of universal gravitation states that all objects in the universe attract each other according to a rule. Okay. The force is always attractive. That is, they always pull, they don't push. Now, of course, there's a very big question. Why does it always pull, no push? Okay, and it wasn't until Einstein that that question got solved. We assume the force acts along a straight line between the centers of the spheres, okay, or the centers of the objects. And the magnitude is proportional to the product of their masses and inversely proportional to the square of the distance between the centers of the spheres. What does this mean? It means that it doesn't matter what the two objects are. You look at the centers, and you will have these forces. In straight lines. Okay. Let's put it in equation format. F equals capital G m1 m2 over r squared, where the constant capital G is called the gravitational constant and has a value of 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared. Write that down on a piece of paper before I go to the next slide. What of Earth, Rayan? No, this is a universal constant. So bear in mind, this is not the same as the small g we have been working with so far. This is capital G. Okay. And to be pedantic, force is a vector. So this is a vector, and it has a direction, which is in the r direction. So this is the magnitude, and this is the force properly defined with the direction. Okay, here's my apple. Here's my Earth. We already see a problem with that. In our previous thingies, we assumed tiny objects. So we just took dot, dot. And if they are far away, we can still use dot, dot. Now we have a problem because this is obviously not a dot and a dot. The apple is tiny compared to the Earth. So how do we use this law with something as big as this? The answer is something called the shell theorem. Okay, I'm not going to go through the derivation of the shell theorem now. We don't have time for that. But what it says is a uniform, spherical. So uniform, that's the first rule. Spherical shell, that's the second rule, of matter attracts a particle that is outside the shell. 3, as if all the shell's mass were concentrated at its center. So basically, we're going back to the concept of the center of mass. If you have a uniform spherical shell and you are outside it, you can act as if everything is at the center of mass. So Earth is a nesting of shells. So we feel the Earth's mass as if it were all located at its center. If you remember from geography or from science, you have the solid core, then you have another core, then you have your mantle, then you have the very, very thin at the outside crust. So we take one huge object and a tiny apple as if they are 2 point particles. Okay. Now, if we actually do the calculation, and we will do a bit of some calculations in a bit, we will find, what did the equation say? F equals GM M over R squared, right? So G M Earth M apple over R Earth squared. And this is the same equation for both of them, which means that Earth pulls at the apple with a force of 0.8 newtons, and the apple also pulls on Earth with a force of 0.8 newtons. Now, at that point, we are back at the same problem, with the truck and the butterfly. How on earth are we having, how on earth, remember, if you remember that problem, how does the butterfly hit the truck with the same force that the truck hits the butterfly? Well, here it is again. How does the earth pull on the apple and the apple pulls on the earth with the same force? Now, the reason is there is no problem with them pulling with the same force, because the difference in mass causes the difference in the apple to earth accelerations. Okay, so we know F equals ma. Now, if force is the same, okay, acceleration equals F over m. So 0.8 newtons divided by, what is the mass of the apple? 100 grams, give or take. 80 grams. Okay, so 9.8 meters per second square. But now if I do the same thing and put the mass of Earth, which is a huge, huge number, the acceleration of Earth will be what? 10 to the minus 25 meters per second square, which is absolutely tiny. Well, this is how we actually get G, Mesa. Yeah, the reason we get G is because F equals MA, and we say it's equal to mg. And we get G by doing F over M. Because its mass is huge. Your force is still 0.8 newtons, but when you divide it by the mass of Earth, which is, billions of kilograms, you get a tiny, tiny number for acceleration. You get acceleration of Earth equals force of apple Earth. We're talking about the acceleration due to the apple pull on Earth. Yeah, very specific acceleration. 0.8 newtons divided by big number equals something as tiny as this. Okay, so the apple attracts the Earth, but the acceleration is tiny, so we don't feel it. But when the Earth attracts the apple, okay, towards its center of mass, which is the center, okay, we feel it because the acceleration is going to be 9.8 meters per second squared. So let's start. I'm going to launch the first PIQ. Okay, so if now you go to that Paul section, you will see that you will have one Paul there. Two objects considered point masses are initially separated by a distance d. The separation distance is then decreased to d over 3. How does the gravitational force between them change? Does it not change since it's only dependent on the masses? Does it increase by 9 times, 3 times, decrease by 3, or decrease by 9? I'll give you about a minute or two to do this because it actually needs a calculation. Here we go. So remember to answer in the pause section. Okay. So those of you who actually did answer in the pause section, about 21, we have 18 people who chose B, 20 people who chose B, 2 people who chose A, and a couple of others. Okay, so the correct answer is indeed B. Okay, so I'm happy to see that more than 90% of the people got it. Okay, so initially you had F equals GMM over R squared, where you are GMM over, well, it's still R squared. Later, okay, you get F equals GMM over R over 3 squared, which is GMM over R squared divided by 9, which is 9 GMM over R squared, which means the force is 9 times larger than what we had at the beginning. Excellent. Okay, so what happens when we have multiple objects? Say we have 1, 2, 3, 4, 5, 6, 7, or you have the sun and then Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, all these planets, okay, going around. Well, since gravity is a force and force is a vector, we simply add them. Okay, if we want the force on this object, we need to find this force and 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 that force. Okay, and then we add them all up. Now these are if we have point particles. If we have real extended objects, okay, then we need to do an integration over all the forces. Okay, so the ideas are still the same that which we have been doing over and over so far. Now, as usual, if the object is a uniform sphere or a shell, we can treat its mass as being at the center instead, center of mass. So if you have multiple real extended objects, you can either do an integration or you can find the center of mass of each one of them and then treat them as point particles. So what is gravity near the Earth's surface? So quite a few of you have been talking about this G constant, yeah, equals 9.81 meters per second squared. So we have Earth with a mass of capital M because it's goddamn heavy, and you have an apple or a small thing with a really tiny mass, M. The distance between them is R, and there's a force F, and it's equal to gmm over r squared. What is this force equal to? If I am looking at it as if I am M, I am this small mass, what is this equal to? Anyone? Okay, so a couple of people have said it correctly. This is equal to mg, isn't it? The one we have been doing overall, right? Or more generally, it's equal to ma, and then we figure out what a is, right? I'm actually going to do it this way. I'm going to say this is equal to ma. Remember, when we had tensions, pulleys, so many different forces, we always said the sum of forces is equal to F net is equal to ma. So this is still equal to ma, second Newton. Now this a is ag, the acceleration due to gravity. So I will equate them. mag equals gmm over r squared. And this m gets cancelled with this m. I end up with ag, acceleration due to gravity, is equal to gm over r squared. This is simply what we have been so far calling g. Okay. So now if we do this calculation, okay, at the Earth's surface, we get 9.81, 9.83 meters per second squared, depending on the location. And I'll explain why the variance in a bit. If, however, I go to the top of Mount Everest, which is about 8.8 kilometers high, I will get 9.80 meters per second square. Tiny difference, tiny difference. What if I take a hot air balloon and go all the way up to 36.6 kilometers? Yep, I will end up measuring 9.71 meters per second square. I'll go a bit higher, up until where the space shuttle goes, 400 kilometers. Bear in mind, this is not an airplane, huh? This is a space shuttle. An airplane cannot go up to a height of 400 kilometers. We get 8.7. Now, if we go to where a satellite are, الأقمار الصناعية, 35,700 kilometers, we only measure 0.225. And this makes sense because we said G equals G mass of Earth over radius squared. Now, G mass of Earth is the same, but my radius is different. My radius here is the radius of the Earth. My radius here is radius of the Earth plus 8.8 kilometers. Here it's plus 36.6. Okay. And so on and so forth. Al-Ayham, interestingly, when do you think it becomes to zero? Let's make it, let's do the equation, yeah? 0 equals GME over R squared. What do you need to make the other side? What do you need to make this side equal to 0? G is a constant, so it cannot be equal to 0. You need equal. You need either the mass to be equal to 0. So option 1, you need mass equal to 0. So there is no Earth. Yeah. Or option 2, your R needs to be equal to infinity. Okay, you have these two options. Either your mass needs to be equal to 0 or R needs to be equal to infinity. So as far as physics goes, the gravitational acceleration or the gravity force due to an object never really reaches 0. It just becomes so tiny, it stops making a difference most of the time at really large distances. Okay, but the only way to have a gravitational force of 0 is either to be at an infinite distance, which is impossible because you're never an infinite away. Okay, or if we don't have a mass in the first place. Now, if we get out of the solar system, for example, we are so far away. Okay, the G of Earth will become very tiny. You will end up with 0.000 something. So for practical purposes, we can say it is 0. Yeah, but for calculation purposes, it's not actually 0. Theoretically, it's not actually 0. Okay, it's like when you have, 3 bezas in your bank account. Now, realistically speaking, in an application form, I might as well have 0 because 3 bezas doesn't buy me anything. Okay, it's absolutely useless. But as far as the bank is concerned, yeah, no, you don't have 0. You have 3 bezas. Yes, Noor. So this is outside الغلاف الجوي. This is also outside الغلاف الجوي, and so on and so forth. Ayham, amazingly not. You would think so, but amazingly not, because it is true. It is amazingly true. Yeah. Okay. Because Noor, you don't need الغلاف الجوي to for the force of gravity to reach you. Yeah, it's just there. Actually, here's an interesting thing, Noor. If the gravity of Earth didn't work outside, if it didn't work outside Earth, we would not have satellite. We would not have, actually, never mind satellite. We would not have a moon. Why is the moon stuck to the Earth and going in circles around the Earth? Because it is bound by the Earth's gravity, right? But it's outside the غلاف الجوي for Earth. So if the force of Earth wouldn't go, force of gravity of Earth wouldn't go beyond the atmosphere, the heliosphere, we wouldn't even have a moon. And trust me, not having a moon is a very big problem. Okay? Everyone literally pretty much dies on Earth if you don't have a moon. Okay. What? Two sections. According to our book, 2. According to the alternative book, Halde-Resnick, 3. Okay. Now the calculated AG, or what we call G, will differ slightly from the measured G at any location. Why? Because the calculated gravitational force on the object, okay, is not going to match its weight for 3 reasons. Okay. Let's see if we can finish 3. Rayan, I don't think we'll finish 3. That's why I'm saying 2. Okay. So the first reason is Earth's mass is not uniformly distributed. Now, if you look at the best models of Earth we have, and this is a very important point. These are models. Okay, we have the deepest hole we have been able to drill into the Earth is the super deep hole that's called the Super Kola in Russia. Okay, and it is about 13 kilometers deep, 13. Okay. We are unable to go beyond that into the Earth. So we have models based on gravity, based on based on magnetic variations, based on a whole bunch of things. But we haven't actually been able to, go into the Earth physically and check. We have a very thin crust. We have a thick mantle. We have an outer core, and we have a really, really dense inner core. Okay, now it's obvious that the densities of these things are not the same. This is way, way heavier than this, for example, in terms of density. Okay. So that's the first reason. Remember when we said F equals GMM over R squared, or when we use the shell theorem, we said it requires something spherical where the center of mass is in the center and it's uniformly distributed. Okay. This is actually the density of Earth's mass. Okay, Noor will come to that in a second. Rayan, I'm not sure what velocity you're talking about. We'll come back to that in a second as well. Okay, so your inner core has a very, very high density. Your outer core also has quite a higher density, but then your mantle, okay, has a very, very low density. And then your surface has almost no density compared to that. Okay. And the density of the outermost part varies from place to place. So, for example, if you have a plateau of Earth that has nothing in it, okay, something like Sahara al-Rub' al-Khali, its density is way different to something like Mount Everest, where there's a lot of weight on that piece. Second, Earth is actually not a sphere. As much as we like to think of it as a sphere, and as since childhood we have had those spheres in our classrooms and we spin them around, Earth is actually not a sphere. Earth is an ellipsoid. Okay? Sphere مفعول شوية. As a matter of fact, the latest computer-generated model of Earth shows it shaped more like a Kamithra, a pear. Okay, an oblate spheroid. Okay. Hello, we're here. شفت كيف إليهم؟ شكله من الكروش في المنطقة. وزننا زايد في عصنا الأرض. Okay. Third, Earth is rotating. Remember what happens when something is rotating? What extra force we have? We have the centripetal force. Yeah? So now you don't only have your gravitational force, you have an extra force. Centripetal force. And since forces are vectors, they will add up. Okay. So what happens when something's rotating? Let's look at the Earth from above. I have a crate, I put it in a weighing scale, and our Earth is rotating. وصارت لي دوخة. Okay, stop. I will have an Fn, right? Now, so far, every time we have had something like this, we simply drew this. We said mg, mg, right? This is what we have been doing so far. Now, if you want to be really, really accurate, that's not really what happens. You have mg downwards. That is absolutely correct. But you also have rotation. So your Fn is actually mg plus m omega squared over r, and this has a minus on it because it's going clockwise. So Fn equals weight equals mg, but my mg is equal to my actual mag minus m omega squared r. So my actual g at that point is my ag, the one that is given by gmm over r squared, minus omega squared r. Let's break this down. Mg is my measured weight. Mag is the magnitude of the gravitational force. M omega squared r is m times the centripetal acceleration. So this is m A centripetal, which is mv squared over r. V equals r omega. So we get m r squared omega squared over r, which is m omega squared r. So Noor AG Noor AG is the magnitude is the gravitational acceleration due to the gravitational force alone. Okay, G is what we actually measure, and it is equal to here. G is what we call the free fall acceleration, NOAD. Okay, G is the free fall acceleration. AG is the gravitational acceleration. So far we have been doing G equals AG, which means so far this is what we have been doing. Okay, we have been taking away the rotation. We're saying there's no rotation, and it's just simply G equals AG. Okay. Now, the reason we've been doing this is because, well, A, this is an introductory course. B, because the centripetal acceleration is small enough that most times it is negligible. Okay. Let's do a few questions to see if we have understood the concepts so far. Okay. So how do I okay, there we go. This is big enough, I hope. Let's start with this PIQ. The Earth's radius is 6,400 kilometers. Your weight in the classroom is W. What is your weight if you were orbiting the Earth in the International Space Station at an altitude of 400 kilometers? So I hope you have been taking lecture notes. If you have not, I will take you back to this slide. At 400 kilometers, the gravitational acceleration is 8.70. I'll give you a minute. Rather quick calculation. Okay. So 11 people out of 18 who did it in the PIQ got it correctly. Who did it in the pulse got it correctly. Okay, I'm happy with that. The correct answer is indeed 0.89. And the reason is very simple. W on Earth is 9.8 times, or 9.81 times M. W in the ISS is equal to 8.7 times M. So WISS over W Earth equals 8.7 M over 9.81 M. The M's cancel out, and this is equal to 0.89 W. Okay, you simply multiply with the gravitation acceleration there. You don't need the radius here because you already know what AG is. You need the radius. Where is R? I don't see an R here. You need the R to calculate AG. But if you already know AG is 8.7, you don't need the radius. AG equals GME over R squared, right? So you need R squared and ME to find AG. But if you already know that AG is 8.7, then you don't need your R. And 8.7 is from this that I opened right at the beginning when I looked at the question, and I told you, look, it's 8.7 at 400 kilometers. So you were given what AG is, 8.7. So here's a question: if the astronauts in the space station actually have a 0.89 W weight in the space station, why is it that in all videos we see them floating? Floating means zero weight. Well, the answer to that is, it's just like when you are on a roller coaster. Okay, in a roller coaster, you're on Earth, you have weight, but when the roller coaster is falling down very, very quickly, okay, you don't feel that weight. So you feel as if you are massless, weightless. Well, it's the same thing here. The astronauts in the International Space Station are actually rotating. They are going around the Earth, okay, and at a constant rate, which means they are experiencing centripetal force and centrifugal forces. So their effective thing is zero. They're constantly falling. Okay. Yes, I have. Exactly, Rayan. Mariam, no. We said no. We said that AG is that according to gravitational force only, and G is the actual one. So when we usually do the questions, yes, it's AG is equal to G. But strictly speaking, if you ask, is AG the same as G? The answer is no. G is AG minus or plus all other forces taken into account. Okay, so G is the free fall acceleration, which is AG plus or minus all the other accelerations taken into account. Okay. Okay. Why does the moon not fall to Earth? I'll give you a minute for this. Why does the moon not fall to Earth? Is it because it generates a gravitational force equal and opposite to the Earth's pull? Is it that the net force on it is zero? Is it beyond the main pull of Earth's gravity? It's too far away? Is it being pulled by the sun and planets as well as by Earth, or is it none of the above? Yes, what? You can. That's why literally we call the satellites Qamar Sanai, because the physics of it is exactly the same the physics of the Qamar al-Adi. Okay. So we have people answering all over the place, as you can see. But what if I tell you that the correct answer is this? None of the above. Okay. So here's what happens. It generates a gravitational force equal and opposite to the Earth's pull. If that was true, and you had two forces that are equal and opposite exactly the same, then it would just stand in its place. It would not go anywhere. But that's not what's happening. It's going in circles around the Earth. So this is not possible. The net force on it is zero. If the net force on it was zero, then again, what is the source of the other forces? Nope, this doesn't work. It is beyond the main pull of Earth's gravity. We just said a couple of slides ago that that is not true because it actually orbits around the Earth. So the Earth most certainly puts a gravity on it. It is being pulled by the sun and planets as well as by the Earth. That is correct, but that is not a good enough reason why it doesn't fall to Earth. Okay, because that would, if we say that these are equal, it would only be equal at one instant, but it's moving all the time. The real reason is, if this is the Earth, and this is the moon, and the moon is going in circle, what is the velocity of the moon? Or what is the direction of the velocity of the moon? It is like this all the time, right? It's tangential. The reason the moon does not fall to Earth is because its velocity is tangential or at 90 degrees to the pull of the Earth. The moon is actually trying to escape the Earth. It doesn't want to be there. The only reason it's still there is because the gravity pulls it all the time inside and gives it a centripetal acceleration inwards, so it's unable to escape. So if A or B or C were true, okay, the moon would simply go away. Just go away. It wouldn't stay in orbit. Okay. Let's do one last question. A ball is thrown from the top of Mount Everest in a direction tangent to the ground. Okay. The initial speed causes the ball to travel in a circular path around Earth. What is the ball's acceleration? What sort of? So an artificial satellite is launched at almost the escape velocity, so it wants to go out. Okay. Because of gravity, it is stuck just like the moon. It keeps going in circles. Okay. All right. Let's see. So 6 people chose A, 6 people chose B, 3 people chose C, and 4 people chose D. The correct answer is G. Once the ball leaves, the only force acting on it is gravity towards the center, right? With acceleration equal to G. It's going in a circular path, so its acceleration is just approximately G, nothing else. That's it. Now, to answer a question, yes, the moon does have a gravity. We said gravitational acceleration, or no, before that, we said force is force of gravity equals G m over r squared. Now, if I am on the moon, G is a constant. R moon. Does the moon have a mass? Yes. Do I have a mass? Yes. So this is what the equation will be. So yes, the moon does have a gravity. Anything with mass has a gravity. You cannot have something with mass that does not have a gravity. You have a gravity. I have a gravity, but it's too tiny for us to notice or to feel. But we do have a gravity. Okay. Yes, exactly as you said. So what happens is the force of gravity of Earth Moon and Moon Earth is exactly the same. The effects are very different though, just as when in the very beginning of the lecture we said, look, it is going to make a very big difference whether the apple is pulling on the, so where to go, I'm trying to find it. When we said, is it the apple going to here? When we said, is the what is the force of apple on Earth and Earth on apple? It's the same thing, but now we're saying moon on Earth and Earth on moon. It's the same force, but the reason, okay, is but the effects are different. Okay, so Earth pulling on the moon with that amount of force causes the moon not being able to escape and go in continuous free fall around the Earth, okay, in a circle. On the other hand, moon exerting that force on the Earth doesn't really move Earth, but it does move the oceans. That is why you have high tide and low tide. Okay. Shema, it all depends on the other forces that are involved. Okay, it depends on the other forces that are involved. So, for example, if we just have the force of gravity and the centripetal acceleration, okay, so you do gravitational acceleration minus the centripetal acceleration because of the directions. Say, for example, however, you are riding on a roller coaster, for example. Okay. So, you know, when you're going on a roller coaster and the roller coaster starts to fall down and you feel as if you're floating, or that sense of your stomach coming up, okay, that feeling of weightlessness, okay, that feeling of weightlessness is because what happens is that fall causes another term here, and we call that minus acceleration of roller coaster. And the total of this would be 0. So your free fall acceleration would be 0, so you will feel as if you are floating. So I'm going to stop the recording now so we don't have a really, really long recording file, but I'll keep on answering the questions that you have.